Hello everyone. In this lecture, we will learn about complete randomized block design or CRBD, which is a type of experimental design in which experimental units are grouped in blocks based on a particular homogeneous characteristic or factor. The purpose of this design is to block or control the variability that may be introduced into the results of an experiment by some extraneous factor, some unnecessary factor. For example, a study on the effectiveness of a drug may be influenced by the age or gender of the subjects. In order to isolate that influence and therefore control the variance in the results of the experiment, a statistician might want to group the subjects by age or by gender, as the case may be. In this lecture, we will first understand what CRBD is, why we use it, how we set up the experiments using this design, and then we will use an example to analyze the data with ANOVA and Tukey method as applicable. So let's begin our understanding of randomized block design by first talking about a block or what blocking entails. Blocking is a process by which experimental units are grouped based on a similar characteristic or a factor that we may think might influence the results of an experiment. So it's grouping together similar experimental units and then randomly assigning the experimental units within each group to a treatment is called blocking. And each group of homogeneous individuals is called a block. So instead of giving the treatment to one group of subjects, we break up the subjects into groups or blocks based on a particular factor which we may think might influence the results of the experiment. For example, the effectiveness of a drug may be influenced by the gender of the subjects. In that case, we will create blocks. One block would be only men, and the other block would be just women. We have separated the subjects based on gender, and then we will apply our treatments on the two groups identically. So if we are working with a placebo and then drug A or drug B, if that's what we are trying to compare, then placebo, drug A, and drug B will be introduced for group A, group of men, and the same will also apply for the group of women. And the experimental units, the individuals, will be selected or assigned to each group randomly. However, the first block will have subjects that are all male, and the second block will have subjects that are all female. So a randomized block design is used when the experimental units are divided into homogeneous groups based on a particular factor that we want to isolate, and those groups are called blocks. And within each block, the experimental units are randomly assigned to treatments. So here we have a workflow of a randomized block design. We begin by creating blocks, which is called blocking, where we create blocks based on a particular factor or a particular characteristic that we would like to isolate. So if we consider that age might be a factor that could influence the results of the experiment, then we would create blocks based on different age groups. Or if it is gender, then we will create two blocks of male and female. And then once the process of blocking is complete, the next step is to use randomization to assign subjects to each of these blocks. But we have to keep in mind the characteristic we used in the blocking process. So if it's male and female, if that's what our blocks are, then the block of males will be a group of men that were randomly assigned to that block, and then for the block of female, it'll be women assigned to that block, but randomly. And then the next step is to apply the treatment to conduct the actual experiment. And then once the treatment has been completed, we will gather the measurements and finally do our analysis on the measurements. Now let's summarize here what we just learned about randomized block design. First of all, it's an experimental design to help isolate treatment effects because there may be confounding variables like age, gender, experience that can distort the results of an experiment. So to block such influence from extraneous variables, we can use the randomized block design. So blocking controls for known sources of variation. So if we know beforehand that these factors can influence the results of our experiments, be it age or experience of the subjects or the age group of the subjects, then we will use the blocking method by that particular characteristic to conduct our experiment. So blocking controls nuisance variables, which is the same as confounding or extraneous variables. It also ensures randomization, and that's very important because in any statistical study, we have to use randomization. All studies or experiments must be based on simple random sample to ensure that the study is unbiased. And also it allows replication. Replication is the process of repetition of an experiment which ensures the reliability of the measurements that we get from repeating experiments. Now again, how does randomized block design help ensure a sound experiment? First, it reduces the variability from known nuisance factors. It increases the precision of treatment comparisons, and then it is ideal when one nuisance variable like age is expected to influence the outcomes or the results of an experiment. So now that we know that a block is a method for controlling experimental error, it is extremely important to make sure that the blocks that are created form a homogeneous group based on the variable that might influence the results of the experiment. For example, if gender is thought to explain some of the variability in the response variable, remove gender from the experimental error by forming blocks of experimental units with the same gender. So one block would be a group of male and the other one would be a group of female. So we have separated our subjects into male and female, and then we will go ahead and conduct the same experiment on each of those blocks. Let's look at an example where we are studying the effectiveness of three types of drugs A, B, and C. And we know that the results of the study may be influenced by the age factor of the subjects used in the example or in the experiment. So the objective here is to compare effectiveness of drugs A, B, C. Then that's how we will just name them. And then the blocking variable would be the age group. So we are going to create blocks based on age groups. There'll be a younger group of subjects within the age group 18 and 35, then the middle-aged group of subjects within the age group 36 to 60, and finally the elderly block would be members that are aged 61 and over. And each age group receives all three drugs randomly. So let's look at the three blocks that were created for our example. The first block is that of the young group, which is 18 to 35 years. Then we have the middle-aged group and then the elderly block. And within each of these blocks, we have three experimental units which have subjects assigned randomly, and the treatments are also administered randomly for each of these blocks. So for the group of young subjects, drug B was assigned to the first unit, drug A was administered to the second unit, and drug C to the third unit, whereas for the middle-aged block, drug C was assigned to the first, drug B to the second unit, and drug A to the third. And for the elderly group, it was drug A, drug C, and drug B. And that administration was done in a completely randomized fashion. So let's now look at the number of experimental units that resulted from creating three blocks of three treatments in each. So for the age group young, we had three Y1, Y2, Y3. That's how we are naming them. And then for the middle aged, we have three subjects as well, three units. And then for elderly also, we have three units. And this is how the drug was assigned. So if we have three blocks and within each block we have three drugs that we are comparing, then we will have 3 times 3, 9 experimental units in all. If there are two blocks and within each block there are 4 experimental units that we are comparing, then we will have 2 times 4 number of experimental units. All right? Now we are going to perform an analysis on CRBD using this example of comparing the effect of 4 different diet treatments in rats. So let's read through it and first understand the problem, and then in subsequent slides we will go through the process of analysis. A researcher is interested in the effect of 4 diets on the weight gain of newborn rats. The researcher randomly assigns rats from the same mother to each treatment so that a set of 4 rats constitutes a block. In blocking by mother, we are removing any variability in weight gain due to genetic differences. The researcher identifies 5 mother rats that each had 4 offspring for a total of 20 rats. For each block or sibling rats, the researcher randomly assigns the experimental units or rats to a treatment using randomly generated integers from 1 to 4. So the study is about comparing the effect of 4 different diet plans on the weight gain of newborn rats. And the researcher identifies that a possible factor that may interfere with the results of the experiment would be their genetics. So they create the blocks based on the mother of the rats in order to remove any variability that might come up due to genetic differences. So that's the purpose of using the randomized block design. So there are 5 mother rats and each of them had 4 offspring, correct? So because they are creating the blocks by the mother of the rats, there are 5 mother rats, so there would be 5 blocks. Each mother would be assigned to a particular block, and within each block would be 4 offspring, correct? So 5 times 4 would give us a total of 20 rats. That would be 20 experimental units, all right? So we are going to look at a picture of the block design, and then we are going to look at the results that come out from this study, and then we are going to analyze that. Now here is a picture of our experiment in tabular form. There are 5 blocks, and each block represents a mother rat along with its 4 baby rats. And each of these rats have been put on a particular diet. And after 6 months, the weight gain was recorded, and these numbers here 15.0, 14.6 and so on, they represent the weight gain, the increase in weight in grams. And we are supposed to perform a hypothesis test to see if there is sufficient evidence to conclude that the weight gains of the rats on the 4 diets differ at the 5% significance level, or alpha equals 0.05, right? So we are testing if the different diets vary in their weight gains on the rats. So we will go through the step-by-step procedure that we learned to perform a hypothesis test, starting with stating the hypothesis. Now for this kind of testing, for block randomized test, we will state our null hypothesis as mu sub 1 equals mu sub 2 equals mu sub 3 equals mu sub 4. The null hypothesis is going to state, or going to assert, that there's no difference in the effectiveness of the diets. And we had 4 types of diets that we were comparing. That's why it's from mu sub 1 to mu sub 4, and all of them should be set to equal to each other. As far as the alternate hypothesis goes, it states at least one of the means is different. So for the alternate hypothesis, you're stating it as a sentence, as a phrase. Step 2 is to determine the significance level, and we have been asked to perform this test at the 5% significance level, so our alpha will be equal to 0.05. Now for our study on randomized block design, we are not going to manually hand calculate the test statistic and all the related data. Instead, we are going to use technology to come up with our numbers, with our F value, the P value, and so on. And that's what we have done here. We have used technology, and we have put all the results in an ANOVA table. So let's spend a little bit of time going through the meaning of these values. Some of them will already be familiar to you from our study of one-way ANOVA, but here in the first column, we always put our sources, and because this is a block design, we have a row for the block. Right, there were 5 blocks, right? 5 mother rat blocks. So the degrees of freedom would be n minus 1, number of blocks minus 1. So 5 minus 1 is 4. That's how we got the number 4 here. For diets, we were comparing 4 kinds of diets. So again, 4 minus 1, number of diets minus 1. So that's 3. That's how they came up with the number here. As for the DF for error, that value is really 4 times 3. It's 4 multiplied by 3 gives us the DF for error. All right, it's not summing it, its multiplication. Now, our study tells us to just compare the diets. We are not interested in comparing the variance among each of the blocks. So even though we have a row representing the numbers for each block, we are going to ignore it for this study. Any analysis of variance table will always have a row for the block, but we can choose to ignore it. All right. So let's go through the rest of the numbers, and for the time being, I'm going to erase this. So we have the DF for diets as 3, and then the sum of squares came up to 51.87 for the diet, and for the error, the sum of square was 36.62. The mean square was 17.29. How did we come up with that? That was 51.87 SS divided by the DF. 51.87 divided by 3 gave us 17.290. As far as the error goes, the SS was 36.62. You have to divide that by the DF, which is 12, and we got the MSE value is 3.052. All right, and then we have the F value as 5.67. What is the formula for F value in ANOVA? It's MSTR over MSE. So MSTR is 17.290, MSE is 3.052. When you divide the two numbers, you will come up with an F value of 5.67, right? And then we have the p-value for a test statistic of 5.67. The p-value is 0.012. All right. And the values in the total row, this 19 for the DF is really the sum of block plus diet plus error DF values, which gives us 19. For SST, it'll be again the sum of 36.62 plus 51.87 plus 14.71 gives us 103.21. All right. So now we are going to go and perform our test using the approaches. We will use the p-value approach here because we have the p-value given to us in this ANOVA table. So let's perform our test here using the p-value approach and come to a decision, which are steps 4 and 5 in the process, right? So we have the same table that we just saw previously. The p-value was 0.012 for the F value related to the diets. So it says over here, we are not interested in whether the weight gains among the blocks are equal or not. We are just interested in the difference in the diet. So we will just focus on the diet row here, right? So we will ignore the p-value for the blocks. That's the reason we are not even looking at the 0.35 number, which is the p-value for the blocks. We will just concentrate on the 0.012 p-value number. So the p-value of 0.012 due to treatment is evidence against the null hypothesis of equal weight gain among treatments, correct? 0.012 is less than the alpha value of 0.05, and therefore we reject the null hypothesis mean, which was asserting that all four means are equal. There's no difference in the diet. Based on the test that we just performed, the ANOVA analysis, we come to the conclusion that there is a difference among the four diets. So therefore, we conclude that the treatment diet does result in significantly different weight gain. However, at this point, that's all that we know. We do not know which diets result in different mean weight gains, right? Which one is greater than the other, which ones are equal to each other or close to each other, and so on. For that, we will have to go into a two-key study. So to determine this, we again rely on the pairwise comparisons of two keys test, right? So the two keys test applies only when the null hypothesis is rejected, correct? And it helps us determine how the means compare with each other. So with the help of technology, we generated three tables here. The two key 95% simultaneous confidence intervals. This is the table with our data, just to keep it in perspective. But the table that was generated by technology are the tables representing the confidence intervals. So diet 1 subtracted from diet 2. So this confidence interval, the first row inside the table is diet 2, then diet 3, diet 4. All right. So look at the endpoints of the intervals has a lower end of -3 and an upper end of 3.5, correct? Now this interval has a lower end which is a negative value and an upper end which is a positive value. That means there's no difference between diet 1 and diet 2. This interval contains a difference of 0, therefore there's no difference between diet 1 and diet 2. Let's look at diet 1 and diet 3. The lower end of the interval was negative 3.4 and the upper end was positive 3.08. Again, one side negative, the other side positive, contains a difference of 0. That means there's no difference between 1 and 3, diet 1 and diet 3. And then the confidence interval for diet 1 and diet 4 is negative 6.9 on the lower end and negative 0.399 for the upper end. So this interval has the same sign for both ends, and that tells us it does not contain a difference of 0. So there is difference between diet 1 and diet 4. And if we look at the p-value results, the p-value for the first row is 0.99, which is pretty high, correct? This p-value is pretty high. So in this case, then we would say that there's no difference, all right? Whereas for 1 and 4, the p-value is 0.02, which is less than 0.05. So that tells us that, yes, there is a difference between these two diets, 1 and 4. Let's look at the next one. 2 subtracted from 3 has one negative end and the other one is a positive, the upper end. So it contains the 0, a difference of 0. Therefore, we can conclude there's no difference between diet 2 and 3. As far as diet 2 and 4, they have the same signs for both ends. So the conclusion should be that there is a difference between diet 2 and diet 4. Let's look at 3 and 4, the confidence intervals of 3 and 4. They have minus for both ends of the interval. Therefore, there is a difference between 3 and 4. Look at the p-value at 0.0365, which is less than 0.05, the alpha value. So we can conclude that there is a difference between diet 3 and diet 4. All right? Now let's look at the graphical representation of the different confidence intervals that we just found and try to understand which diets differ from each other and which diets do not, right? So let's try to understand this picture. On the horizontal line, we have the differences shown. 0.0 represents a difference between two means of 0. So this dashed line shows where that difference of 0 is located. To its left are all the negative differences. To its right are all the positive differences. And each of these horizontal lines within the picture, these are the confidence interval, the lower end, the upper end, and this dot at the center represents the point estimate. All right? So let's try to understand how to interpret this picture. Now, the first one over here represents the difference between diet 2 and diet 1, right? So this is the confidence interval that was created by using diet 2 minus diet 1. And we see that this interval contains a difference of 0. There is a difference of 0 contained within this interval. If you read the writing here, it says if an interval does not contain 0, the corresponding means are significantly different. In other words, if the interval contains a 0, that means the means are not significantly different. They are close to each other, all right? So the confidence interval for 2 minus 1 contains a difference of 0. This dashed line passes through this interval. That means there's not much difference between diet 2 and diet 1. Right? Let's look at the next one, which is 3 minus 1. Here too, we see that this confidence interval contains a difference of 0. So that tells us that diet 3 and diet 1 are not significantly different. As for diet 4 and diet 1, difference of 0 is not contained within this interval. This dashed line is outside of the interval, so that means there is a significant difference between diet 4 and diet 1, correct? Then 3 minus 2, again, this interval, diet 3 and diet 2, this confidence interval contains a difference of 0. That tells us there's not much difference between these two diets. 4 minus 2, diet 4 and diet 2. Yes, there is a difference because 0 does not pass through this interval, and the same for 4 minus 3. So the conclusion is there's a significant difference between diet 4 and the rest of the diets, but not as much between diet 1, 2, and 3, right?